So, I think in my last class I proved this theorem that a 2n by 2n real symmetric positive definite matrix gamma corresponds to the covariance matrix of a bona fide n mode state if and only if gamma plus iota by 2 omega greater than equal to 0, right. This is what we have discussed, where this gamma is of course the jkth entry is the average of R j R k, because I have taken this R j rho to be 0 without loss of generality we can take it, and sigma j k is equal to the iota sigma y plus anyway. So, it is like this matrix. Okay. So, it is like 0 1 minus 1 0, then 0 1 minus 1 0, 0 1 minus 1 0, rest of these things are 0. So, all these are 1 2 3 up to twice n. Okay. So, this is what we have proved. Right. So, what we are going to do today is I mean, of course, this we discussed earlier also, that by Williamson's theorem you can cast it like this gamma can be transformed into S gamma S transpose, which is diagonal form, like kappa 1, kappa 1, kappa 2, kappa 2, kappa n, kappa n. Okay. And this is the Williamson's canonical form, and S is a symplectic matrix SP2 n R. But the question is that how to get this symplectic matrix. Okay, that was the question. So, what we are going to do today is to understand what sort of transformation on the phase space can give rise to such a symplectic transformation, so that you can have this diagonal form. Okay. And we said already that this symplectic matrix, okay, so these will correspond to a unitary transformation, where this unitary transformation is generated by some Hamiltonian, where this Hamiltonian is quadratic in nature. So, basically this is sum over j and k is equal to 1 to twice n. Let us say I call it as H r, because this is real element, j k, then r j and r k hat. See this r j, so r vector, so this is your like x 1 x p 1 etcetera x n p n, and this is a Hermitian matrix. So, H j k r is equal to H k j star. This is a Hermitian matrix. Okay. So, this is my Hamiltonian, quadratic Hamiltonian, which will generate this thing, this unitary. So, what we are going to discuss today is how to get such a diagonal form through, I mean this is the most general one, because we do not know what will be the actual form of this. So, what we want to figure out is what specific choice of this Hamiltonian one can make, so that you can get this diagonal form. Okay. So, this is basically the idea. Okay. Yeah. So, as I discussed for the single mode case, there are essentially two types of such Hamiltonian. Okay. Single mode case, so essentially two types of such Hamiltonian. One is that, let me take it like H is equal to say theta. Now, this 4 factor is because of some calculational purpose, I could have taken just theta. This is a dagger A plus a dagger, and you remember this is something like rotation in phase space. Okay. So, this is my Hamiltonian, and how does it change? So, because of this relation 1. So, this is your, what will be this? This is theta by 4 twice a dagger A plus 1. Okay. And now, you can figure out what will be the action of exponential of, let us say I apply this iota h, then this x, then exponential of minus iota h. Okay. And you can figure out from here that this should be of this form. So, x is this a dagger plus a by root 2. So, you can figure out from here that this is of this form, that this is x cosine theta, whether it will be plus or minus we will have to see whether. So, let us say this plus, we can figure out from here exactly what will be this thing sine theta, and similarly for p it will be minus I h is equal to, this is minus x sine theta plus p cos theta, something like that. Okay. Maybe here it is minus, here it is plus, we can see that, right. So, therefore, the transformation, symplectic transformation is basically this one, cosine theta sin theta minus sin theta cosine theta, which will take this x p to this thing. Okay. Right. Now, this is simply a rotation in phase space. So, this forms this rotation group SO2, right, 2 dimensional rotation group, right, it rotates. So, single parameter family, and H is the generator of this group, because it is a single generator, and we know that this is a compact group. Okay. So, what is the meaning of compact group?
That the limits are attained.
Yes, yes.
Once the limits to a point, then that point is attainable in the group.
Exactly. Yes. So, if I take these rotations, okay, and take a sequence of this rotation, and the limit it will be another rotation. Okay. So, this is a compact group. Okay. Right. And we have discussed that this transformation is energy preserving transformation, in the sense that this H is, of course, it will commute with the number operator, because this number operator itself is this A dagger A. So, therefore, this is a passive transformation, right, because it does not change the number of energy. So, this is a passive transformation, and examples of such passive transformations are like lossless beam splitter, right. This is a passive transformation. I mean, rotation of course is a passive transformation, right. Anyway, so the point is that this is one particular type of Hamiltonian generating this symplectic transformation, and this is a compact group. Okay. The other one is this thing, let me call it as maybe what maybe let us say z by 4. See, 1 by 4 I will take outside. This is let us say A dagger square plus z star A square. Okay. I mean, z is in general complex, but you can take it to be real also. So, this you agree that this is a Hamiltonian, right. Z is a complex number, and now you can do this thing I h x exponential of minus iota h. Okay. I mean, using this formula, that this will be what, this is x plus 1 by factorial 1 iota h x plus 1 by factorial 2 iota h comma iota h x, so on and so forth. Okay. So, anyway, so if you do that, what you will get is something like this. Yeah, so this is what we need to do. We cannot just say that this is what you will get. You will get. So, we know that if it is, say, let us say z is equal to is a real number. Okay. Let us say, in this case, this is something like cosine hyperbolic. So, now I should be careful. So, this so this is actually, it should be cosine hyperbolic r by 2. Okay. I mean, you can figure out, it is not so difficult. Cosine hyperbolic r by 2, this is no, sorry, I am talking about x, right. Okay. So, maybe I will do it for a. Okay. So, then this will be cosine hyperbolic r by 2 a plus iota sine hyperbolic r by 2 A dagger. I mean, this one can figure out whether it will be r by 2 r etcetera. I think it should be r by 2. So, if I take r is equal to z is equal to r, and correspondingly if I take this one, of course, A dagger exponential of minus I h, then this should be your minus iota sine hyperbolic r by 2 A plus cos hyperbolic r by 2 A dagger, something like this. Okay. And so, you can figure out what will be exponential of iota h x exponential of minus iota h, and this should be basically, you know, it should be a dagger plus a by root 2. So, what will be that? A dagger plus a by root 2. So, this should be 1 upon root 2 cosine hyperbolic r by 2 a dagger minus iota sine hyperbolic r by 2 a, and plus with a it will be cosine hyperbolic r by 2 a plus iota sine hyperbolic r by 2 a dagger, something like this. So, this will be basically x cosine hyperbolic r by 2. Oh, no, it should not be the case. I think I have goofed up something. Okay. So, actually it should be like x should go to e to the power r or minus r x. Okay. Maybe this is not the correct one. Any whatever be the case, you can do it. I am not going see this. I think I have done it earlier. Okay. So, maybe I will just write down the result, that will be better. Okay. So, so maybe I will just erase this part. So, basically what you will have is so e to the power iota h, maybe I will just write the result, that will be easier. Yeah, there is no point of doing it every time, you know. So, I will just write down the result, it will be easier. Yes. Yeah. So, okay. So, what I have taken is something like this. Yeah. So, this is, so my h is, so let me write it like this. So, this is, say this h is let us say this is r. Okay. So, this r by 4 this thing. So, it is for real r. Okay. So, then what you can figure out is that so exponential of minus iota h and then x exponential of plus iota h. Okay. So, if you do that, then it should be something like x cos hyperbolic r by 2 plus p sin hyperbolic r by 2. So, r is real here, if I do that. Oh, yeah, right. Okay. And similarly, exponential of minus iota h p exponential of plus iota h, this should be equal to x sin hyperbolic r by 2 plus p cos hyperbolic r by 2. Okay. So, if I look, so now we see that what will be the corresponding symplectic transformation, which will take x and p to this one, whatever I have written, x cosine hyperbolic r by 2 plus p sin hyperbolic r by 2 and x sin hyperbolic r by 2 plus p cosine hyperbolic r by 2. And this is basically your, so this matrix, symplectic matrix is cosine hyperbolic r by 2, sin hyperbolic r by 2, sin hyperbolic r by 2, cosine hyperbolic r by 2. Okay. This is my symplectic matrix. Okay. Right. So, this is an element of SP2R. right. So, this symplectic transformation is achieved by such a Hamiltonian. Now, this group is not a compact group, it is a non-compact group, okay? Because if we look at this actually maintains the angle between two vectors in two dimension, right. That is how it becomes a compact group. In fact, you can say that this also maintains the distance between 2 points. On the other hand, here this does not maintain that distance or angle, rather it maintains these the Lorentz distance in 1 plus 1 dimension, one space one time dimension. If I look at the distance, so like what is that? This will preserve area, but you can think in terms of distance also. So, if I take the proper orthochronous Lorentz transformation for one space one time dimension, then that distance, what is that called, this x square minus t square or something like that, right. Yeah, x square minus c square t square or something like that, right. Yeah. So, that distance will be preserved by such a transformation, by this transformation, and and as a result this is a non-compact group. Okay. I mean, one can also prove it separately, that if you take some limiting sequences, then its limit may not be an element of this. So, anyway, so this is a non-compact group. Okay. So, but this is of course a special case, because the most general case in this case will be something which you obtain. So, so this is squeezing about so this is squeezing about quadratures like x and p, but for the general case where you have like 1 by 4 z and z star, this corresponds to squeezing together with rotation, okay, like whatever we have done there. So, squeezing plus rotation, you can do first rotation and then squeeze, or you can do squeezing and then rotation. Of course, these two will give different results, but essentially the thing is that z is, you can write z as something like r e to the power I theta, right. So, basically this r part will give rise to the quadrature squeezing, and this corresponds to also squeezing, but in a rotated frame. So, you can give squeezing to now here and here. Okay. So, the rotated quadrature you can do, right. So, and this also is a generator of this, basically this is also generator of this group. Okay. I mean, what happens is this group is actually isomorphic to this group SU 1 1, which is the the group of matrices 2 by 2 matrices, let us say, where I mean this will keep this Lorentz distance fixed. Okay. And this is also the group of SL2C. Okay. So, the spatial linear transformation in 2 dimension.
Excuse me, sir.
Yes.
Generally, I take the Hamiltonian for
Yes.
squeezing to be something like a square minus a dagger square.
Yes. Yes.
And then I see that x simply transform as e raised to power minus r times x.
Yeah. So, here it is not like that.
Yes, it is like
It is not like
because
that.
the Hamiltonian is different.
Yeah, of course, because the Hamiltonian is different, but essentially this is also squeezing.
Yes, yes.
You will have to rotate it in this frame. So, x plus p by root 2 and x minus p by root 2, or minus x whatever, minus x plus.
Yes, yes, yes.
So, So, it corresponds to that. Okay. If I take this a dagger square plus a square. Okay.
Okay, it is a rotation is also included.
Yes.
Okay, thank you.
Yes. Okay, good. So, essentially for single mode case, if I look for quadratic Hamiltonians, I will have two such classes. One is this type single parameter family which generates this group compact group. The other one is this type which is two real parameter family, because Z is complex, or you can say R and theta, and that also generates this non compact group. Okay. And that is all for the single mode case. So, this idea we will have to use now for multi mode case. Okay. So, this I mean, so in multi mode case we will have to split this group, this SP 2 n r. So, it will have basically generators n into 2 n plus 1, that one can count this many generators, and n square of them corresponds to the compact group. Okay. And remaining n into n plus 1 corresponds to non compact group. Okay. And this compact group, in the case of single mode it is SO2, in the case of n mode it is basically this UN, okay, the group of n cross n unitary matrices, or and so there also we will see that the generators are something similar to this. Of course, we will have to consider n modes, and in the case of non compact groups, yeah, so this group is bit complicated. I can write down the generators, and from there one can see what are the what should be the non compact group. Okay. Yeah. So, yeah, so this is basically the idea that from single mode case how will you generalize to the n mode case in terms of the generators, namely the Hamiltonian, and then see what sort of physical transformation will give rise to such a diagonal form. Okay. So, that is basically the idea. Okay. So, if I take this, so the question is now that we have already discussed that if gamma is a 2 n by 2 n real symmetric positive definite matrix, the necessary and sufficient condition that this will correspond to a covariance matrix, bona fide covariance matrix, is this thing, right. This is what we have proved. Now, what we want to prove is that, so that means it will correspond to some n mode state, right. Now, what we want to prove is that when can I say that this state is not an arbitrary state, but this state is, this involves some amount of squeezing, in the sense that you have some simple minded state, maybe it is a coherent state or something like that, and from that coherent state I want to apply some unitary corresponding to this the symplectic transformation, right, and then I can, I mean this is not necessarily coherent state, you can take also thermal state, it is fine, and then this will involve some amount of squeezing. So, you see we are we are so now we are basically restricting our search domain, because here earlier it can be any n mode state, right. I mean it can be Gaussian, even for non Gaussian state also it may be possible. Now what we are assuming is that can it be something like, so I have some initial state rho 0 which may be Gaussian, non Gaussian, etc., and I will get this rho by action of this unitary which corresponds to squeezing. Okay. When I say squeezing, it should involve not only that squeezing transformation, but also this rotation, because this is also, why this will involve, because I said that this rotation will generate squeezing in rotated quadratures. Okay. So, therefore, you cannot neglect this. So, the question is that, and why. So, the question is, once this is satisfied, what extra condition one should impose on this gamma, so that the corresponding state will have some amount of squeezing, that is the question. Okay. Now, why are we interested in that? Because you see we said that the canonical transformation is generated by quadrature quadratic Hamiltonian, and quadratic Hamiltonian, as I said, it should be some sort of squeezing, right. So, what sort of density matrices can be generated by such squeezing transformation? So, that is the idea. Okay. Okay. Is it clear? So, therefore, now our focus is not arbitrary canonical transformation, our focus is on those, I mean symplectic transformation which can be generated by quadratic Hamiltonian. Okay. Is that fine? Okay. Good. So, the question is that what sort of properties such a gamma should have, so that I can say that look, it involves some amount of squeezing. So, if I can show that if I look at the diagonal entries, let us say j j, diagonal entries of this gamma, and if I figure out that this is less than half for some j, I mean here of course this condition is satisfied, this is a real symmetric positive definite matrix, etc. So, this says that if you remember the single mode squeezing case, what happens is that the variances, okay. So, you can call it variance, covariance, etc. So, the variances, one variance, so the variance in one quadrature will become less than half, one quadrature will become greater than half, right, for squeezing, is not it? That is the idea. So, therefore, this corresponds to, if for one j this happens, of course, it cannot happen for all j, because then it will violate the uncertainty relation. So, if this happens for some j, then we say that of course, this rho is squeezed. Now, what squeeze it is, whether it is squeeze vacuum, squeeze coherent state, squeeze thermostates, squeeze rotated thermostat, etc., that one can figure out, but some amount of squeezing is there. Okay. And therefore, it can be achieved by this quadratic Hamiltonian. The question is, what happens if this is greater than equal to half for all j? So, this is a bona fide covariance matrix, but still if this condition is satisfied, what can be said about squeezing? Okay. And this may be, I mean this can hold good. I will give you one example where this holds good.
But then we can't say conclusively whether there is squeezing involved or not.
Yeah. So, therefore, you will have to go in deep. I mean, so you will have to look for further details to see. Is this clear? Okay, good. So, let me give you this example. So, let us take gamma to be of this form half cosine hyperbolic r sine hyperbolic r sine hyperbolic r cosine hyperbolic r, and here I have taken r to be positive. Okay? Right? Now, if I look at this, of course, this is a positive definite matrix. Do you agree with me? For r positive, cosine hyperbolic is positive, and the determinant of this is 1/4, 1/4, right? 1/4, not half, isn't it?
Minus
Minus
I
I square x.
is 1.
Oh no, what is the determinant? Cos square, cos hyperbolic square minus sin hyperbolic square. So, that is what is 1, right?
Yes, that is one, but I think the prefactor is to the power of dimension. Like when you take half inside, there's half in each of the terms, right? Cos hyperbolic by 2, cos hyperbolic by 2. Right?
So, this is 1/4, right? So, basically it is 1/4.
How did it become 1? Half times.
So, what is cos hyperbolic r minus sin hyperbolic r? Is it not 1?
That's not.
Cos square minus sin square is 1.
But when you take the determinant, the prefactor, here it's half, it becomes half squared because it's a 2 plus 2 matrix. So think of it this way, when you take the half inside, like it becomes cos hyperbolic by 2 and cos hyperbolic by 2 in their diagonals. So when you do that, it will become cos square hyperbolic by 4 minus sin square hyperbolic.
Oh, you are saying the eigenvalues are 1/4.
No, not eigenvalues. The determinant of this, let me write it like this.
Okay. Yeah.
Okay, yes. So, this is 1/4, right? Right.
Not just the matrix, but half times the matrix.
Of course, yes.
Okay.
Yes. So, iota by 2 omega, if I look at it, what is this? This is basically gamma plus iota by 2 0 1 minus 1 0, right, and this should be what? Cos hyperbolic r by 2, then sin hyperbolic r by 2 plus iota by 2, sin hyperbolic r by 2 minus iota by 2, cos hyperbolic r by 2. And what is the determinant of this? Okay, again this is a, these are positive, and the determinant of this gamma plus iota by 2 omega, what will be that?
Minus 1/4.
1/4 plus 1/4.
Then there is a 1/4 also.
Yes. 1/2.
0.
0.
1/2.
1/2.
1/4 plus 1/4.
Careful, this is,
Yeah, it's 1/2.
1/2, right? Yeah. So, therefore, this is also positive definite matrix. Okay. Okay, good. So, this is positive definite matrix, right. So, So, therefore, you see that it satisfies these condition of the result that I mentioned, and as a result there exists a single mode state rho such that the covariance matrix, I mean this its covariance matrix is same as gamma, right. This is what this theorem tells us, because this is a bona fide covariance matrix, it satisfies this condition. Okay. Now, let us look at the diagonal entries of gamma. So, gamma 1 1 is equal to gamma 2 2 is equal to half cos hyperbolic r, and because r is positive, this is always greater than half, right. So, therefore, you cannot say whether it is squeezed or not, is not it? You cannot say that. So, but how to see that whether squeezing is there or not, right. Okay. So, for this what you can do is you can take the state alpha colon eta or r, whatever you want to call alpha colon r, which is the squeezed coherent state. So, this is iota r by 2 a dagger square plus a square acting on the coherent state alpha. Okay. So, this is squeezed coherent state. Right, and if you look at this Hamiltonian, this is of course, so the Hamiltonian is basically, if you want, r by 2 or minus r by 4 or minus I by 4, whatever you want to call, a square, a dagger square plus a square, right. This is your Hamiltonian. So, this is so this is the Hamiltonian that I considered, which is active Hamiltonian, because it does not preserve the number operator, does not commute with the number operator, right. So, now if I look at the covariance matrix, okay. So, this is my state, squeezed coherent state. So, what I want is so this is my Schrodinger picture. So, I will have to, for operators I will have to take the Heisenberg picture. So, let us take this thing exponential of. So, what I want is I want these. So, let me call this as so rho is alpha, I mean the projector on this state, okay, squeeze coherent state. Okay. So, what I want is this thing gamma rho, which is whose jkth entry is basically half rj rk rho. I mean, because the mean values I have taken to be 0, you can calculate the mean value anyway, it is not a problem. So, essentially, so rj rk, so r vector, because this is a single mode case. So, this is actually x and p, right. Okay. So, therefore, now let us consider, I am doing it in the Heisenberg picture. So, minus iota h. So, h is that r by 4. So, r by 4 a dagger square plus a square, and then so okay. So, maybe let me write it in this way, why I am doing this thing. So, what I want is this one x square with respect to rho, because the average value is 0, I have taken the mean value, right. I mean, you can calculate, but p square and then half x p plus p x and half x p plus p x. So, this is the matrix, right. This is my gamma rho. Okay. Right. So, now if I look at let us say x square with respect to rho. So, which is alpha colon r x square alpha colon r, and this is basically alpha exponential of minus iota r by 4 a dagger square plus a square, and then this is x square, then exponential of iota r by 4 a dagger square plus a square acting on alpha, right. You look at the definition of this alpha comma r. So, what we want is this expression. So, this is like a squeezing transformation. So, anyway, so if you, so what you can figure out is that exponential of minus iota by 4 a dagger square plus a square acting on x, and then exponential of iota by 4 a dagger square plus a square, what you get is the following: x cosine hyperbolic r by 2 plus p sine hyperbolic r by 2. Okay. Similarly, if you do this thing exponential of minus I by 4, oh sorry, here it should be, where is the r, r should be here, otherwise it does not make sense, r should be there. So, r by 4 a dagger square plus a square, then p, and then exponential of I r by 4. So, what you get is x sine hyperbolic r by 2 plus p cos hyperbolic r by 2, okay, which is this transformation that I have written somewhere else. So, you see this gives rise to this following symplectic transformation, which is like here. So, cos hyperbolic r by 2, sine hyperbolic r by 2, then sine hyperbolic r by 2, cos hyperbolic r by 2. So, this is the symplectic transformation, and this is an element of sp2r. Okay. Right. So, so this is the basically the squeezing Hamiltonian that you have obtained, and now if you calculate this quantity, this gamma, this covariance matrix for this state. So, I am not going in through the all the details. So, if you calculate this covariance matrix, what you get is the following: half cosine hyperbolic r, sine hyperbolic r, sine hyperbolic r, cosine hyperbolic r. And remember, this is the matrix that we started with. Okay, this is the one which we started with. So, you see that acting on this coherent state, which is of course a Gaussian state, you apply the squeezing transformation to get the squeezed coherent state, and the covariance matrix of this is this one, in which of course every term, these diagonal terms are greater than half, but still we know that you can achieve that state by the squeezing transformation. Okay. And yeah, so this is basically the idea that if you provide, if somebody provides you a bona fide covariance matrix, it may or may not be achieved by this quadratic Hamiltonian, squeezing Hamiltonian, if at least one diagonal entry is less than half, you are sure that this can be achieved by squeezing. But if it is not, then you will have to look at it carefully separately and figure out whether it is the case.
So earlier, like we had seen that if we given a covariance matrix, there can be different rows that can lead to that covariance matrix.
Exactly.
So this is one example of a state which leads to this covariance matrix.
There can be some other states
which is not squeezed.
which is not squeezed. Yes,
So that is possible.
that is also possible. That is also possible. Okay. So let me first let me write down. So now you have this idea that so you know what sort of quadratic Hamiltonians are there, at least for the single mode case, which can give rise to squeezing transformation. And I am not neglecting rotation, because in order to squeeze in a rotated direction you need rotation. Okay. So now I go to the n mode case. So this group sp2nr, you can think of it as the defining representation of this is this set of matrices S. S is a 2n by 2n real matrix such that S omega S transpose is equal to omega, right. This is the defining representation, I mean defining representation of this group sp2nr. I mean it means that there can be other matrices means not just 2n by 2n, there can be other higher dimensional matrices or so forth, which can also satisfy this thing, but this is just the defining representation as we do in the other cases also. Okay. Like for SU2 we say that the defining representation is a 2 by 2 special unitary matrix, but it can be something else. Anyway, so now the question is how many real parameters are there to characterize such a matrix, let us say. So this is a matrix which has how many real parameters, which has how many entries, 4n square, right, because 2n by 2n real matrix. So 4n square entries are there, 4n square real entries of course, because this is a real matrix. Now how many of them are independent? So you remember this, so let us say S is equal to S j k, j and k is equal to 1 to 2n, right. So then this condition S omega S transpose is equal to omega, this is equivalent to, so if I look at these entry j kth entry, this should be j kth entry, right, and this is S j alpha omega alpha beta and then S k beta, right, because transpose of this, yeah. So this should be equal to omega j k, and here it is sum over alpha and beta is equal to 1 to twice n, right. Okay. So now the question is how many parameters you can have. So, for n is equal to 1, let us say, how many real parameters you will require? So, for s is equal to, for n is equal to 1, this sp 2 r, this is area preserving transformation. Okay. So, if I take A, B, C, D, so area preserving transformation means acting on any vector. Okay. I mean, basically if I take this vector as, let us say, x1 x2 real vector, and this vector as y1 y2, the area, so that means this, what is that called, parallelogram. So, this area should be preserved under this action. You can say also angle preserving. Yes.
No, but the length also should be preserved.
Length has to be preserved also. So, this is area preserving means length has to be preserved. Yes, yes. So, what is this area in terms of vector? What is that called?
Length of these two times sine
No, there is a
theta.
vector. What is that called? Is it the dot product or cross product mod? Cross product, right? Yes. Yes. So, the cross product. So let me call it as x and this as y. So, x cross y, this should be constant, right? Yeah, this should be constant. So, what sort of, so this is a real 4 by 2 by 2 matrix. So, what sort of constraint this will impose on it? Yeah, basically it is the determinant condition. Okay. So, AD minus BC should be equal to 1. Okay. Sorry? Actually, it is 1 because this is SP, it has to be 1. Okay. So, therefore, you see that the number of real parameters, independent real parameters to specify this matrix is 3. Yeah, so this thing is old. It is 1. So, basically it is n into 2n plus 1. So, which n is equal to 1 case of course satisfied with 3.
N is equal to 2n plus 1 independent parameters.
Yes, real parameters will specify these matrices.
So that is n into 2n minus 1 dependent conditions.
Yes.
Because if you start 4n square with this, then that will be n.
But how many independent conditions are here? So, this.
So how many constraints does this put? Then we can subtract it from.
Yes,
4n square.
yes.
So that is n into
Total is 4n square. So, you can subtract these constraint from there. Yes. So, how many independent conditions are there? So, that is what one should figure out.
considering the symmetries of omega.
Yes, yes, yes. Considering the definition of omega. So, this is one can count here. So, total is 4n square, and then you will have to subtract. How will you get this one? So, you will have to subtract minus 2n square minus n. I think so. Yes.
Yes. So 2n square minus n is basically 2 into.
Yeah. So, this is n into 2n minus 1.
That is 2n into 2n minus 1 by 2.
Exactly.
So 2n into 2n minus 1 by 2 is basically the number of upper triangular matrix, then how many it is? Because the lower
Because that is
triangular is
lower
just
also it can be
specified.
specified by the same thing. Okay.
Like one part of along the diagonal you have to consider all the
Exactly.
entries on that side,
Yes.
including the diagonal.
Yes. I mean, if I take this is a 2n by 2n matrix, so
So the upper triangular, either that or the lower triangular, because
anyone,
yes, anyone, including the diagonal.
including the
So
diagonal.
that is 2n plus 2n minus 1 plus 2n minus 2, like that.
Exactly,
series,
exactly.
and the sum of that geometry.
Exactly. Yes. Yes. So you understand the basically the logic is from this relation you will have to figure out how many independent constraints are there. So, and then that you can subtract from this 4n square, which is, so this is the number of independent constraints and that you subtract from here. So, the remaining one is this one. So, this many real parameters you will require to specify any element S. Okay. So, this is why it is called n into 2n plus 1 parameter group, or you can say that because this is a continuous group you will require this many generators. So, you know, so that you can write things in terms of infinitesimal elements. Okay. Okay, good. So, now let me write down the compact generators. Well, compact generator means the generators generating a compact subgroup, maximal compact subgroup of sp2nr. Okay. That is what we will have to figure out, compact. In the case of single mode, there is only one compact generator, okay, which is this rotation. So, let me write it down. These are, this 1 by 4 is for just for just ease of calculation. So, nothing more is there. So, this is aj dagger aj plus aj dagger, j is equal to 1 2 3 up to n. Yes, right. This is what you will have. These are, so how many of them? N. Then you have 1 by 4 aj dagger ak plus ak dagger aj. Now, this time j and k is equal to 1 2 3 up to n and j is less than k. So, how many of them?
N into n minus 1 by 2 or n plus 1 by 2.
For 1 it is, so if I choose j is equal to 1, you will have n minus 1 k, right. If I choose j is equal to 2, it will have n minus 2. Okay, so, you will have to add them.
Yeah, that is n into n minus 1 by 2.
Yes. So, this is n in number, this is n into n minus 1 by 2, right, the number of subgenerators. I think so, yes. And you will also have, so look at this, this will provide you single mode rotation, right, rotation, single mode rotation, right. This will provide you lossless beam splitter. This we have seen, right, like a dagger b plus a b dagger, something like that. So, this is lossless beam splitter. This one again j and k is equal to 1 2 3 up to n and j is less than k. Again this is a beam splitter, but you will have to do rotation, rotated version of beam splitter. Okay. So, this is also a lossless beam splitter, and this is now, this number is again, this is n into n minus 1 by 2. All these are Hermitian operators. So, if you remember, this is something like this corresponds to the double oscillator representation of these SY, right, or JY, whatever you want to call JY. Okay. This is double oscillator representation of Jx, and this is the total number operator, I mean something similar to that. So, anyway, so this, so therefore, you have basically here it is n, here it is n into n minus 1. So, therefore, total, so n square compact generators, or you can say n square number of generators generating a compact subgroup of this sp2nr. So, these are the generators generating the maximal compact subgroup of sp2nr. I mean you cannot have a larger compact subgroup of this sp2nr. Okay. Right, and these are all passive generators. Why passive? Because all of them will commute, they commute with the total number operator, namely this one, j is equal to 1 to n aj dagger aj. So, if you take any one of them and commute with this n, which is the total number operator, you can see that all of them will commute with n. So, therefore, this will give rise to passive transformation, energy preserving transformation. Okay. So, look what generalization we have made in terms of the, when you go from single mode to n mode, this is anyway it is simple, it is sticking to the single mode cases. This is the generalizations that we have made, and this is by incorporating the beam splitter operation. In the single mode case there is no beam splitter operation. Okay. So, we have already exhausted n square. So, total number of parameters is, so n into 2n plus 1 minus n square, which is n square plus n. So, which is n into n plus 1. So, we still need to figure out n into n plus 1 number of generators, right, and what are they? So, one particular type is 1 upon 4, this is aj dagger ak dagger plus ak aj, I mean you could have written aj ak also fine, and this is j k is equal to 1 2 3 up to n with j less than equal to k. Remember, squeezing requires aj square also, right, single mode squeezing, aj dagger square plus a square, aj square. So, this involves single mode squeezing as well as two mode squeezing, right, if I take 2 modes together, and then this is also squeezing, which is aj dagger ak dagger minus ak aj, same thing. So, both of them will give rise to squeezing. I mean you will have to rotate in some case, like here you will have to rotate, or here you will have to rotate. Okay. And what is the total number then? For this case the number is n into n plus 1 by 2, right. Here also it is n into n plus 1 by 2. So, the total is n into n plus 1. Okay. So, therefore, you have obtained all these generators and this will give rise to, and these are all I mean non-commuting with n, which is sum over j is equal to 1 to n a j dagger a j. So, therefore, this will give rise to active transformation. Okay, and this is squeezing, right. So, these are the transformation corresponding to, and this will correspond to a non-compact group, okay, the non-compact generators. In fact, you can also figure out from the fact that none of them will commute with n. So, this is the set of n square compact generators, that is the set of n square plus n number of non-compact generators, okay, right. And therefore, any transformation, and one can also argue that all these n into 2n plus 1 generators are independent. One cannot achieve one from the other, these are independent generators. Okay. And so, what you can think of is you can write down any element of SP to n r, okay, which is okay. Let me ask you this question: will identity or something proportional to identity be an element of this?
If the state itself is in that form, time form.
No, this is about the transformation. I am not talking about the state. This is the group. I said that this R is equal to 0 corresponds to identity. Yes, yes. So, this is the group of matrices 2n by 2n matrices such that S omega S transpose is equal to omega. So, can I say that S can be identity?
Yes, that is trivially true. Right?
It's not a generator. I mean, generator we usually
Yes.
do not bound.
That is true. That is true. But it will be an element of this group, right? Okay. So, the way we generate elements of compact group is that we start from the identity and then little bit give a displacement, right. I mean displacement mean in the sense that we change the parameters little bit step by step. Non-compact group case it is not so easy, you cannot do that. But anyway, I mean any operator can in principle be achieved through concatenation of unitaries generated by these Hamiltonians, right. Whether you will require in one go, like let me call these Hamiltonians, like you can call them as H1 etc. H n into 2n plus 1, right. So, whether it can be achieved by something like this, like exponential of let us say minus I alpha 1 H1, then exponential of minus I alpha 2 H2, something like that, but it is not necessarily always of this form, some form of this. Okay. Yeah. Anyway, so now that we have classified these the compact and non-compact generators of this group, now for us it will not be difficult to figure out that given a bona fide covariance matrix, that means which satisfies this, that means it corresponds to some rho, whether this will be achieved by some transformation on some rho 0 on S transpose, where this S corresponds to some unitary which is generated by generators of this of this kind, okay, what I mentioned here, either of the compact form or non-compact form or their combination. Okay. Okay, good. So, this is what we are going to discuss maybe in the next class. So, basically what, okay, so let me look at this group for the more single mode case SO2. We said that this is generated by the rotation, right. The Hamiltonian, whose Hamiltonian is something like this, theta by 4 A dagger A plus A dagger, right, something like this, which will generate the rotation. So, this is a single parameter family and this is a compact group. Okay. Now, for n mode case, the problem is that, so therefore, this is a compact subgroup of this sp2r. Do you agree with me? This is a group and this is a compact subgroup of this, right, because all these elements are elements of this. Question is that if I take this group SO2n, so SO2n means 2n cross 2n real orthogonal matrices, the group of that. So, if I take this group, can I say that this is also compact, you can figure out this is a compact group. Can I say that this is also an element, a subgroup of compact subgroup of sp2nr? In other words, the question is, if I perform any rotation in this 2n dimension phase space, will that be an element of this? Is this question clear? And this will be important to figure out these eigenvalues of this covariance matrix and all that. Okay. Okay, you can think about it. It turns out that no, not every element of these is an element of this. Okay. There are something which lies outside of this. For example, you can take the 4 dimensional space 2x and 2p. There you can come up with some rotation, orthogonal matrices which are not element of this. So, which does not give rise to symplectic transformation. Okay. So, what we will consider for this case is basically this one, this SO2n and then the intersection of sp2nr. So, basically we are looking at the elements of this sp2nr which are also rotations. Okay. And these are the, so this kind, so this will be also a symplectic transformation, and this sort of symplectic transformations will help us to keep the eigenvalues of this covariance matrix intact. Okay. Right. So, and this is important to get this Williamson's form, right. So, this is why we will concentrate on this intersection. Okay. So, we will concentrate on the symplectic transformations from this intersection. Of course, we will go beyond that also, but to begin with we will concentrate on that, and what sort of generators one should consider, and what sort of symplectic transformation that can give rise to, and what sort of canonical forms of these covariance matrix one can get out of that. That is what we are going to discuss. Okay. Right. So, yeah, so this is our basically the goal, that to figure out generators of this intersection. Okay. Okay, good. So, I think I should stop here. So, next day I will discuss about that, and what I will also discuss is, so I already considered this gamma, which is a real matrix, and that is why I will call it as gamma r, and then I will also consider its complex version gamma c, and then I know that how does it transform. So, it transforms as gamma r s, where this is also real, the symplectic transformation, and we will see how it transforms. I will call it S c gamma c S c dagger here. Okay. So, S c is the corresponding complex symplectic transformations, and this will be required to understand the generators of this intersection also. Okay. So, this complexification of the symplectic transformations and also the covariance matrix we will have to figure out. Okay. So, let me stop here, and yeah, if you have question, yes.
So also it's true that SO2n has 4 n square generators, right? Because here we calculated that it's n square for
Yes.
SON.
Yes, yes,
This has 4 n square, whereas that is n into 2n plus 1.
yes,
That has even fewer generators than an SO.
exactly, 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 yes, yes. Yeah, generator wise, of course, that is true.
I mean, from there one can draw the conclusion that it cannot be a simple minus, because
Yes, yes,
it
of course.
would have
But for n is equal to 1, it is the case.
yeah, for n is equal to 1 is fine.
Yes.
Because then 2n.
No, it is not. It is not. Yes. Yeah. Okay, good. Thank you.